Hi, hello. We are from Group 3, Team B from Section 3, and for this video, our group will describe or explain about the hardenability test throughout the video. First of all, for introduction. For heat treatment, hardenability is a very useful and important property of steel. It determines the rate at which the given steel could be quenched. This also talks about the maximum hardness that can be achieved on the surface of steel or larger cross-section bars subjected to drastic quenching. The Jominy and Quench test is used to determine a steel's hardenability, which is a measure of the steel's ability to harden in depth under a specific set of conditions. Steel hardenability information is required to be able to choose the proper combination of alloy steel and heat treatment to manufacture components of various sizes in order to minimize thermal stresses and distortion. This test determines whether each part has the same hardenability or vice versa.
Hello and good day everyone. My name is SATHESH son of GUNASEGARAN and my matrix number is AA201052. And today I will explain about the procedure for hardenability test. So the first, we must prepare a cylindrical steel specimen with a measurement of 25.4 diameter and 100 mm length for an quench process. Next, expose the steel specimen to a specific temperature for certain period of time to produce austenite steel. Then remove it and mount one end of the steel to quench it with water jet or specified flow rate. Third, Vickers hardness test machine is used to file along the specimen after it cooled down to get a flat surface. The steel specimen is clamped at Vickers hardness tester with applied force of 50 kg. The screen of Vickers hardness tester provides a microscopic image. Look through it and observe the two parallel lines on the steel specimen. The line is moved till the both lines are slacking together, then press the reset button. Place the specimen at the base of the hardness tester and then adjust its position close to the indenter until it makes contact. The start button is pressed and left until the indicator switch off automatically. 6. Move the stage down and adjust it to the center. Look through it and move the stage up until the stein is visible. The measurements on steel specimen is done by moving the line at the each of the corner. Press read button to gain the value of D1. Turn the lines to other two corners and gain value of D2. As the last step, record all the values of the hardness of the steel specimen. The distance from quench end is taken account for every 3 mm consecutively from the quench end.
A very good afternoon. My name is Taranjit Singh, metric number AA2018, and today I'm going to proceed to explain the graph obtained from the Jominy and Quench test. Based on the graph of HRC against the distance from quench end of the mild steel specimen, it can be observed that the HRC value decreases when the distance from the quench end increases. The distance closest to the quench end has the highest Vickers hardness test value, which is 55.4 HRC. This shows that there is a complete transformation of austenite into 100% martensite. The quench end has highest HRC value due to its high martensite microstructure. This proves the theoretical explanation on how hardenability of the specimen changes from the distance of the quench end. To explain this further, we will go to the TTT diagram. From the TTT diagram, when the Vickers hardness test is carried out at 0 mm, the hardness value is at the highest as the microstructure cools rapidly from austenite to 100% martensite. Martensite has highest hardenability compared to austenite and pearlite due to its BCT crystal structure, which is body-centered tetragonal. The BCT crystal structure has few slip planes that makes it to exhibit maximum hardness, but at the same time it is brittle. The short time of cooling process reduces the carbon diffusion into the martensite microstructure, hence increasing the hardness of the specimen. Next, the HRC value continued to decrease further due to mixture of martensite and increasing pearlite content, whereby pearlite microstructure is a ductile and tough microstructure. Hence, this will influence the mechanical properties of the steel specimen, having both hard and ductile properties. More cooling process time allows the carbon to diffuse into the specimen. From 12 to 15 mm, as we can see from the table, there is a drastic decrease in the hardness value. There is a very major difference in the hardness value This is probably due to during that formation, there is a very less martensite formation take place. Instead, there are more transformation from austenite into fine pearlite. This makes a specimen to possess higher ductility and toughness with less brittleness.
My name is SRIKOOHEN, matrix number AA200317, and today I will be explaining the discussion for question number 3 until question number 5. Question number 3. Give factors that influence hardenability curve. There are 3 main factors which influence the hardenability curve: carbon content, grain size, and alloying elements. Increased amount of carbon content hardens the specimen. Besides that, alloying elements such as nickel, chromium, and others retard diffusion of carbon in steel, thus forming martensite. When grain size is increased, it retards the diffusion of carbon and forms martensite, similar to alloying elements. Question number 4. Discuss the difference in hardenability curve between the specimens that quench in water and oil at the same temperature. The hardenability in specimens that quench in water will be higher than the specimens that are quenched in oil. Water quenching is rapid cooling, where water as a quenching medium that extracts heat much faster, while oil will extract heat much slower. Rapid cooling retards the diffusion of carbon in steel, thus forming martensite, which is hardened. Question number 5. A cylinder bar with 25mm diameter and 100mm long is austenized in a furnace followed by a quench in still water. If the entire specimen is immersed at the same time, predict the produced graph of hardness versus the distance from end of bar. The value of hardness and distance from bar end is going to be almost same, thus producing an uneven line when graph is plotted. The cooling rate will be the same along the length of the cylinder bar, which is rapid cooling. So the values indicating hardness of the bar will be close as possible. They will not be exactly the same because some portion might have developed different microstructures. For example, the highest value from the graph indicates that portion has high volume of martensite. Meanwhile, the slightest drop in the value indicates the portion might have developed ferrite or pearlite microstructures.
So for the last one, conclusion. The hardenability test using the Jominy and Quench test helps to determine the hardness of the steel specimen at each surface after heat treatment on the material, such as annealing and normalizing. To select steel for a heat-treated component, it is important to know their hardenability. Alloying and microstructure both affect their hardenability, allowing the correct steel and quenching rate to be selected. The prior processing of the steel also affects the microstructure and should also be considered. These tests help engineers to classify material based on its hardenability so that it will be much efficient to identify the specification of each material to be used in various fields. Next, for the recommendation, there are a few precautions and recommendations to enhance the accuracy of this experiment. For example, during heat treatment, wear goggles and heat insulator gloves to prevent spark from furnace hitting hands that led to injuries. During quenching process, locate a specific amount of time on the steel specimen that correspond to the heat treatment temperature. Quenching beyond or before the specified period of time can alter the steel microstructure. Use proper tongs according to the type of work. The intender of the viscous machine should be examined first to ensure there is no limit. Diamond pyramid shaped indenter is recommended to use because diamond has high hardness and wear resistance, which makes it a good abrasive. Hence, the indenter does not deform easily without fracture or damage.